Hello, Hornets. Welcome and thank you for joining me today. Today I'm going to be going over how we find solutions to quadratic trigonometric functions. Now, let's just take an example, one that's not that difficult. Let's go ahead and look at, let's say, let's do cosine squared x plus sine x equaling 1. We're going to solve that. So the first thing I'm going to do is recognize that sine cannot be changed without doing something extra. So cosine can be replaced. We know that cosine squared of x has to equal 1 minus sine squared x, which means that I can put 1 minus sine squared x in for the cosine squared of x, and then put our sine of x behind it, equaling 1. Now, our goal is to set it equal to 0. I personally like to move my sine squared so that it's going to be a positive. That means that I'm going to be left with 0 equals sine squared of x minus the sine of x, and this is going to eat, and this is my, notice the 1 minus 1 will go away. Here I can now see that sine of x can be factored, and I'm now looking at sine of x minus 1. Well, if I'm trying to get it equal to 0, when does each of these factors, sine of x and sine of x minus 1, equal 0? Well, we know that the sine of x is going to equal 0 at 0 pi and pi on our basic unit circle and our domain of 0 pi to 2 pi, which is most likely what we would have. If we have infinite numbers where we don't have the domain, I would now add my period. So that would be 0 pi plus 2 pi k and pi plus 2 pi k. Solving for the sine of x minus 1 would be sine of x equal to 1. And we know that the sine of x is going to be equal to 1 at pi over 2. We now have all of our answers that are between 0 pi and 2 pi. And therefore, my solution set would be 0 pi, pi over 2, and pi. If I did not have this domain, I would immediately attach the period times k. So 0 pi plus 2 pi k, pi plus 2 pi k, and pi over 2 plus 2 pi k. We just make sure that we add k as an element of the integer set, and we have all of our solutions. Now, these constitute all of the solutions that are outside and well within the domain that was originally given. So if they just ask for any solution, we make sure we add our period. Alrighty, let's go ahead and take a moment and let's look at another quadratic. This time, we're going to make it a little bit harder. What happens if it's not in the unit circle? Oh my goodness me. Let's take a look at tangent squared x minus 6 tangent x plus 5 equal to 0. Now please take note that our solution, let's go ahead and say it is between 0 pi and 2 pi. Now, I personally like radians. That's because I work with trig all the time in calculus. And if I were trying to do it in terms of physics, I would be using degrees. Notice that I don't like tangent. I just don't. So I'm going to use the dummy variable u. I use u when I'm replacing expressions, and I use alpha when I'm representing angles. So in this case, I'm going to let u equal the tangent of x. Well, since we have tangent of x, the quantity squared, minus 6 times the tangent of x, plus 5 equals 0, I can just replace it entirely. And you'll notice I can now have a function that I can work with. And it factors quite nicely. U minus 1 u minus 5. That means that I can now back substitute, and I'm now looking at the two binomials, tangent of x minus 1 and tangent of x minus 5 equals 0. If I want it to equal 0, either one of these factors can be 0. So I have the tangent of x minus 1 equaling 0, and the tangent of x minus 5 equaling 0. Tangent of x is now equal to 1. Well, when is that going to happen? That's going to happen when I have pi over 4 reference angle, and if I add pi to it, which is my period, I will find the second one, and that would then be in the third quadrant at 5 pi over 4. Notice this is a standard angle, and I'm now going to set it equal to theta, or x. We're looking between 0 and 2 pi. So my first answer is pi over 4. Second answer is going to be 5 pi over 4. And let's see if I can find a third answer. That would be 9 pi over 4. And unfortunately, 9 pi over 4 can't be used because it's beyond our domain. Tangent of x equaling 5. This is where we have to use our calculator. So I'm going to be in radian mode. So make sure you're in radian mode. Radian, oh, there we go. Let's put in mode. Radian mode. And here we go. Second quit. Zoom in on this a little bit so you can see it clearly. Let's make sure we clear everything. And I'm now going to do second function tangent of 5. Enter. Now we know this is in our first quadrant, and we know our period is pi k. So I'm looking at x equaling, and now I'm going to zoom back out, 1.3734 plus pi k. My first answer is 1.3734, and my second answer is going to be found by adding pi to it, and that would be 4.5150. Please make sure you round to the fourth decimal place. I now have several answers. The first answer is pi over 4. The second answer is 1.3734, followed by 5 pi over 4, followed by 4.5150. Notice that we can have a solution that is either non-standard in the unit circle or an answer that is not in the unit circle. Either way, we have to make sure that we give exact values when we are able, and we find non-exact values when we have no other choice. And this is finding the solution of a quadratic. Now, be aware, sometimes quadratics can be much, much more difficult. Let's see if I can't find one that's going to give us a little bit more of a problem. And I have several to choose from. So I'm going to go ahead and I'm going to turn this over, and we're going to find one that's a little bit more tricky. And there went my lights. You'll notice I'm now in darkness. This is our wonderful district in all of its glory. So let's go ahead and work with -3 secant of theta plus cosine theta is equal to -2 root 3 secant theta cosine theta plus cosine theta. Now, my goal, if I can put that down there, is to try to find the solution between 0 and 2 pi. So 0 pi less than or equal to theta is less than 2 pi. And we're now ready to try to find our solution. All righty. So let's go ahead and solve. That means that I'm going to take the cosine and I'm going to subtract it on both sides so that I have -3 secant theta is equal to negative 2 root 3 secant theta cosine theta. And I'm going to move the 3 secant theta over, or I'm going to move the other one. I like this 3 secant theta moving. So I'm now going to have 0 equals 3 secant theta minus 2 root 3 secant theta cosine theta. I'm now going to go ahead and factor. So I can factor out the secant theta, and that leaves me with 3 minus 2 root 3 cosine theta. Each one has to be equal to 0. So when is secant theta equal to 0? And when is 3 minus 2 root 3 cosine theta equal to 0? Now we know that secant theta is going to equal 0 when cosine is also, let's see, let me think about this. Oh, it's not going to work. There's no time. Remember, our secant looks like this, and at no time is it ever going to touch this axis. So this portion has no solution to it. Let's look at this one now. If I have solving, I have negative 3, and I'm going to divide by negative 2 root 3 is equal to the cosine of theta. Double negative becomes positive, multiplying by root 3, and I end up getting cosine of theta is equal to, and I have root 3 over 2. Well, we know cosine is going to be equal to root 3 over 2 at a reference angle of pi over 6. This happens in the first quadrant and the fourth quadrant, so the two answers are pi over 6 and 11 pi over 6. And those are my two solutions between 0 and 2 pi. And that is solving a polynomial equation. In this case, it wasn't quadratic, as we had factored out the cosine, or the secant. And that would be my answer for this wonderful problem. Now, all functions can be solved. In most cases, they'll either be no solution or they'll give us a solution. And we go through this basic process of trying to get it equal to 0, factoring out any GCF, and then taking each factor and setting it equal to 0 and solving. Once we have it solved, we move on. Now, the next step is for us to combine multiple solutions to this idea of finding solutions between 0 and 2 pi. If you have questions about this, please make sure you ask them. I hope this has given you some insight as we work with our solving quadratic trigonometric functions and finding our solutions that we get between 0 and 2 pi. Thank you very much, Hornets. I hope this was positive for you. If you liked it, please remember to click like. That'll give me an idea. If you have suggestions or comments, please feel free, and I look forward to what you have to say. Thank you very much. Be well, take care, and have a very good evening. Good night. Cheers.